Earth's magnetic field. Earth's magnetic field near the ground is typically 0.5 Gauss, where 1 Gauss is 10 to minus 4 Tesla. In temperate northern latitudes, this field is inclined downward at an angle of approximately 45 degrees. Consider the feasibility of using the Earth's magnetic field to enable the levitation device shown in figure. So here you can see we have a bar, so we're going to lift this copper bar here. The magnetic field, due to the Earth's magnetic field, has a horizontal component that is into the page, and the diameter of our bar is D, length is L. All right. Part A, estimate the current needed to lift a copper bar with diameter 5 millimeters using the horizontal component of the Earth's magnetic field. The density of copper is 8,900 kilograms per meter cube. Okay, so the bar obviously has a weight, the gravitational force pointing down. If I use the right-hand rule, L cross B, so the L vector is in the direction of the current, so my right hand forefingers point in the direction of the current, and then they are curled towards the magnetic field. The thumb points upward, so this tells me that the magnetic force is pointing upward. So for it to levitate, it should basically balance this gravitational force. All right. Now, what is the magnitude of the gravitational force? It is the weight of the copper bar, which is the density multiplied by volume, which is pi r square, where r is the radius, area multiplied by length, that's a cylinder, and multiplied by gravitational acceleration. The magnitude of the magnetic force is I L B, because L vector and B vector are perpendicular to each other. And if I call this the y-axis, this is my y-axis, then the net force on the y-axis should be equal to 0. So net force on the y-axis should be equal to 0. Which means that ILB should be equal to rho pi r square LG. The L's will cancel, so you can see that these L's will disappear. And I will find the current I need to be rho pi r square G divided by the magnetic field. But r, the radius, is not given to me. What is given to me is the diameter. So this can be rewritten as the current is equal to rho pi d square G divided by 4b. Why? Because the radius r is equal to d over 2. So that's the current we would need. Now, if I plug in the numbers here, I have to be careful about this magnetic field because it should be the horizontal component of the Earth's magnetic field. So I should take the Earth's magnetic field and multiply it by cosine 45 degrees to find the horizontal component. Okay, so let's plug in the numbers. The current I would need is the density 8,900 kilograms per meter cube. Pi, diameter was 5 millimeters, 5 times 10 to minus 3 meters square, multiplied by gravitational acceleration 9.8, divided by 4 times 0.5 10 to minus 4 Tesla multiplied with cosine 45, which is square root 2 over 2. So that's our magnetic field. And if you calculate this, the current turns out to be 48,000 amperes. It's a rather big current you would need in order to levitate it using the Earth's magnetic field. Part B. A copper bar with diameter 5 millimeters will melt if it carries a current greater than the fusing current of 900 amps. Is it feasible for our device? Well, the current I calculated that I would need is 48,000 amps. So since I see that 48,000 is greater than 900 amps, this is not feasible. So this device cannot be built this way. Let's move on to part C. Estimate the minimum strength of the magnetic field needed to levitate our copper bar. So obviously it's not 0.5 square root 2 over 2, but what would it be? Well, if the current is, the maximum current I can reach here is 900 amps before it melts. So if I have a current of 900 amps, you can see that this is maximum current I can have. The minimum magnetic field I would need in order to have this levitation device, using this expression here, B is equal to rho pi d squared G over 4 I max. So the minimum magnetic field I would need would be rho pi d squared G divided by 4 maximum current I can have. And I can calculate this. How much is that magnetic field? The minimum magnetic field I would need is 8,900 kilograms per meter cube pi the diameter squared, 5 times 10 to minus 3 meters squared, 9.8 meters per second squared, gravitational acceleration, and 4 times the maximum current is 900 amps. So this gives me a minimum magnetic field of 1.9 millitesla, which is 19 Gauss. So instead of the 0.5 square root 2 over 2, I would need 19 Gauss magnetic field for this device to work if I allow 900 amps current to pass. So just before it melts, then it's going to levitate. Part D. Suppose we use easily obtainable 1 Tesla permanent magnets to supply the horizontal magnetic field, and suppose our bar has length 10 centimeters. Estimate how much extra weight we could levitate with our device using a current of 10 amperes. Okay, so if I put an extra weight here, you can see that the magnetic force I will have will be balancing the weight of the bar plus this extra weight. So in part D, my equilibrium condition, the magnetic force FB is equal to ILB, because they're perpendicular L and B vectors, is the weight of the bar, rho pi R squared LG, plus the extra weight, W extra. So the extra weight I can have, W extra, is L times L parentheses IB minus rho pi R square G. So if I substitute the numbers here, the length is 10 centimeters, 10 times 10 to minus 2. The current is 10 amps, magnetic field is 1 Tesla, minus 8,900 kilograms per meter cube, pi the radius squared, so let's make this a square parentheses, the radius squared 5 times 10 to minus 3 millimeters is the diameter divided by 2 squared multiplied by 9.8 meters per second squared. So that gives me the extra weight, and the extra weight I can handle would be 0.83 newtons with this calculation. So here I have the magnetic force FB basically pointing upward. Then I have Fg, the gravitational force, which is the weight of the bar pointing downward. And then I have this extra weight pointing downward, W extra. So that's basically what the magnetic force is balancing. All right, so in this problem, we looked at the feasibility of a levitation device that can use Earth's magnetic field horizontal component. You can see that when the magnetic field horizontal component is into the page, L cross B, right hand, 4 fingers pointing in the direction of current, curl towards the magnetic field into the page. The thumb points upward, so it will be opposing the gravitational force on the bar, and it can levitate if we reach equilibrium. So then we can say basically the magnitude of the magnetic force, ILB, should be equal to density multiplied by volume, which is the mass of the bar, multiplied by gravitational acceleration. So this gives us the current we would need, and using the magnetic field's horizontal component, because it makes 45 degrees with the horizontal, cosine 45 times 0.5 Gauss, this gives us 48,000 amperes. And that current turns out to be too high, because at 900 amperes this bar will melt, so it is not feasible. So if the maximum current it can handle is 900 amps, then what would be the magnetic field needed for it to work? If we calculate this using this expression, solving for the minimum magnetic field, substituting maximum current, we find 19 Gauss. Suppose that we can have a 1 Tesla magnetic field. Then the question is, how much extra weight can we levitate? Well, the magnetic force will be balancing the weight of the bar plus the extra weight, and using this we can calculate the extra weight that we can handle to be 0.83 newtons.